This is section 11.2. We're going to talk about how to do inference for a correlation coefficient, and we're going to use the simulation approach. As always, pause and look at the learning objectives. So let's remember our Facebook example that we're doing in our last section. Researchers wanted to know if having a higher number of Facebook friends is related to higher brain density in a specific region. So here was our plot. We already looked at it. We said, oh, it looks like having more friends is associated with a higher density. Like as friends goes up, density also seems to go up. We like to use the word tend there. Like we're not saying cause and effect, but we're saying, oh, friends goes up, density also tends to go up. Okay. The correlation was 0.366. So we have some correlation. If we were to draw an oval around it, you can see it's not super tight to a line. Okay, but we do seem to have a very distinct pattern here. Okay. But that is just for our sample. What we want to do in statistics, for everything we've learned usually, is say, well, what does it tell me about the population? So we're interested in knowing if we have evidence that having more friends is associated with higher brain density in the entire population, not just in our sample. Okay. So we might want to think about what we call our population correlation rho. This is the Greek letter rho. Okay. We use that for population correlation. So the 0.366 is the correlation for our sample. We're interested in trying to estimate or make inferences about our population correlation rho. Let's see. So we did steps 1 through 3 in our last section of the 6-step process. So today we're going to start at step 4, which is make inferences beyond the data. So there are two options basically here. So we know that we saw an association in our sample, okay, but now for our population, there's two options. So in our population, option number 1 is that there is not a relationship. And our observed association and correlation of 0.366 in our sample was just due to the chance of who happened to be in our sample, okay? So maybe there's really no relationship, but we just happen to pick a sample full of people that made us think that there was an association. The other option is that there really is a relationship between the number of friends and brain density. Notice we are not saying cause and effect, just that they're associated. Okay, because we can't say cause and effect unless we have a nice randomized experiment. So we need to decide if our observed association of 0.366 in our sample could have happened just by chance if there was truly no association in the population. So to do that, we have to do our 3S strategy. And we don't always call it this in every section we've been doing, but it's what we've been doing it, even if we didn't actually tell you each time. So the 3S strategy is first we find a statistic. So we can use our sample correlation of R equals 0.366 as our statistic. That's our sample correlation. Then we have to simulate. So I say, well, if there's really no relationship. So if there's really no relationship, that's the key words here. We're saying, let's pretend there's no relationship at all. Then we can consider that it was really just coincidence which Y values went to which X values. So what we do to simulate is we shuffle up all the Y values and just randomly reassign them to the X values. So in our situation, we're going to randomly shuffle up all the brain density values and just randomly reassign them back to the number of friend values. So to do this, we're going to go to our ISI applets. We're going to go to quantitative and correlation regression. So we go to quantitative correlation regression. And we can select our data. Facebook is already built into it. Click use data. Now double check, do you have the right X and Y values? Because otherwise you'll need to switch it. So we have friends on the X, density on the Y. That looks right. We're going to click shuffle options. Right now we just want one shuffle. We're going to shuffle the Y values. So you can see this is my data over here, is my original data. Then right here, it will show me a new plot. Okay, so basically it took all of the Y values and just reassigned them to X values. And so now instead of looking like I have this nice cloud of points going in a certain direction, I seem to be very scattered around. Okay, so this is the plot of my shuffle data. I can also click data, okay, of my shuffle data, and it will show you the X and Y values. So let's actually come back to what I have printed on here. I want you to notice that before friends, when the X was 0.3 for number of friends, my density was negative 2.4. Now when X is 0.3, my density is 0.75 because I reassigned my Y values. So all of my Y values are all just mixed up. So when I did this previously, after I shuffled it, I got one shuffled correlation. So this is my most recent shuffled correlation of 0.0774, and it plotted that over here. Okay. And you do have to choose statistic correlation. By default, it does slope, which is another way that you could do simulations, but it's not the way that our book does it. Okay. So you do have to choose correlation. I can't tell you how many times I've forgotten that while I'm making notes. Remember to click choose correlation. Okay. But you can see this is the one correlation that I got. And then I put the plot of the most recent shuffle here so you can compare. So our original data looked like this. It definitely has a form, okay? But my shuffle data kind of just looks like a big oval. I can't really tell like what it looks like. It seems pretty random. My correlation looks like it's pretty close to 0. Okay, specifically 0.0774. Okay, so let's go back and look at what we got this time. Okay, so this time I got a shuffled correlation. Oh, I didn't do it. So choose statistic, you have to choose correlation. Again, I told you I keep forgetting. Okay, so my most recent shuffled correlation was 0.1326. So let's try again. If we shuffle the y values again, now just know my x for 0.3 has a different density. Okay. My new correlation is negative 0.0949. If I change it to the plot, again, it looks like it's pretty randomly scattered. Here's my new shuffled correlation. So I could shuffle my y values again. I get a different correlation. Again, they seem pretty random. Okay. And my correlation is negative 0.16, so it shows up on my plot. I could shuffle again. New correlation, negative 0.18. New point on my null distribution. And I can keep shuffling, and every time I shuffle, it will give me a different correlation. It puts a new point up here. So let's just try a few more times. So again, every time, watch the correlations change down here. Watch a new point up here. So every time I shuffle the y values, we get a new correlation. And we just keep doing this. We just keep shuffling the y values to say, well, what correlations do we get if we just randomly shuffle them? So if there's really no association, I should be getting correlations close to 0. Every once in a while, I might actually get a pretty big one. Okay, and that's really just what happened to be in our sample. Okay, we get surprising results occasionally. Okay, and we just keep shuffling, and eventually we're going to get tired of doing that. And we might want to try it a few more times, like 10,000 times. And so we can shuffle our y values again. And that will take a moment. So let's come back to our notes. Okay. So I do want you to again notice, if we randomly shuffle and assign our y values, then the shuffle data is going to have a correlation pretty close to 0 usually, and the scatter plot is usually looking like there's no association. Okay, because, and this is the important thing that you should memorize, if there's no association, we'd expect the correlation to be about 0. So we want to try 10,000 shuffles, which is what I just asked the applet to do. Okay, but here's what I have here so you can remember it. Okay. Here's all of my different correlations. This is called, again, if you've forgotten, this is our null distribution. It's what we would expect if there's no association or if the null is true. So our sample correlation was r equals 0.366. So let's color in the region on the null distribution that would correspond to our p-value. To do this, let's remember what direction did we think it should be. Okay. So we thought, the association would be positive. Not from looking at the plot, but because of their original question. Because they said they thought Facebook use would increase the density of this brain region. Okay. And so because we thought the association would be positive, we're going to look for our correlation or anything higher. Okay. So we're going to use our applet to count how many times our shuffle gave us a correlation 0.366 or higher. Again, that was based on our hypothesis that we thought the association would be positive. So we'd come up here on our graph and find 0.366 and find everything to the right. Okay, because again, the original conjecture was the association would be positive, so we want to look to the right. So what is our p-value? Let's go back to our applet. We want to count our shuffles greater than 0.366. Okay, and in case you've forgotten, if you didn't remember what that is because I didn't write it down, you can click this box right here for correlation coefficient. So I click correlation coefficient, And then you can see that our correlation is 0.366. Okay, so coming over, we want to count shuffles greater than or equal to our sample correlation 0.366. Make sure you have the greater than or equal to. We click count. This applet is a little bit slower with such big, even though they're not really big sample sizes, but it's a lot more work to shuffle the Y values. So it would be okay if you just did 1,000 on this applet. Sorry, 1,000 repetitions. So it looks like this time, when I shuffle it, I got a count of 109 out of 10,000, so 0.1019. So our p-value is 0.0109. So how do we interpret our p-value? That means the probability of observing our sample correlation coefficient of 0.366 or higher, that's what we got in our sample, is about 0.0109 if the null is true. So that means if there is no association. So does that seem plausible? Do you think that there's no association and we just happen to get our sample correlation of 0.366 or higher? I would say that this does not seem plausible. That is a small p-value. I think there probably is an association in the population. Okay, and because we have that small p-value, we could say something like, we have strong evidence, it's not below 0.01, so just strong evidence that there is a positive, so it's a positive association because I did a greater than hypothesis here, that there's a positive association between number of friends and brain density. Now, let's go to step 5 and talk about some conclusions. So we could say something like, again, we already wrote it once, but we could say we do have strong evidence that a higher number of friends is associated with a higher brain density in that region. Okay, you do have to be careful to use the word associated, okay, because we do not want to say cause and effect. Okay, so let's skip to this. We are not saying cause and effect because we don't have an experiment with random assignment. We're just saying they're associated somehow. There's probably confounding variables that we aren't thinking about, that maybe there's absolutely no cause and effect. Maybe it's truly just this other confounding variable. Maybe it is cause and effect. Like, we can't really say, so we just say associated. Okay, but we can still use that relationship to make predictions. And maybe there are other avenues of research that would open up just knowing that there is a relationship. So it's still useful information, but we can't say cause and effect. Okay, and let's make sure we say that we can only generalize this to a population similar to the sample of volunteers, not for all people because it wasn't a random sample. Okay. And step 6 is always look back and ahead. So we could say things like, well, maybe we should try another study with a random sample. So we could generalize. Okay, and well, is there a way to make it random assignment? Like, I don't think there's really a way to control how many Facebook friends someone has. But it would be great if we could have had a random assignment, some random experiment somehow, and maybe we could think of a way. Okay. It would be interesting to do a randomized experiment that controls how much time someone spends on Facebook. Like, that's a different question than just how many friends you have. Maybe that's really what's causing these changes, is how much time they spend on it, not how many friends they have. Or we could also look at how Facebook use is related to brain density in other regions of the brain instead of just this one region. Those would be possible things you could put in your paper if you were writing a paper about it. So now that we've done the work, let's talk about what the official hypotheses would be. So our population correlation is rho. Okay, I know it looks like a P, but it's called rho. It's the Greek letter for R, which is why they picked that one instead of like a fancy looking R, because it actually is the Greek letter for R. Having a correlation of rho equals 0, a population correlation, means that there is no linear association. Remember, correlation only measures linear association, so you do need to put that in there technically. Okay. So the null hypothesis is that there is no association between the two variables. And we don't write this every time, but again, we mean no linear association. Okay, so you say no association, the null in symbols would be that rho is equal to 0. Sorry, that is definitely a typo. Rho equals 0. And then the alternative is that there is an association between the two variables, but we can break that up. We have 3 options, okay? The first is that it's a positive association, okay? That my population correlation is greater than 0. Okay? Or you could have a negative association, which would then be your correlation is less than 0. Or it could just be an association, which is just not equal to 0. So this is what we do when we don't know if it should be positive or negative. So if you don't have a previous hypothesis that it should be positive or negative, you just say an association and you just look in both directions. Okay. So again, if you don't know if it should be positive or negative, you just say there's an association and you check for positive correlation and negative correlation. So again, as a remark, unless you have a randomized experiment, you cannot say cause and effect. So be very careful to not sound like you're saying that changing the x values will cause the y values to change. Okay. Today we're only looking at a simulation-based approach. There is a theory-based approach for testing if there's a linear association, but in the interest of time, we're going to skip it for this course, so you don't have to worry about it. So let's think about our Facebook study and write down what the hypotheses are. So remember, our research question is, does having more Facebook friends swell, that means increase, the size of brain regions devoted to tracking and maintaining relationships? Okay. So that tells me the increase means they were hoping or assuming or proposing that there's a positive association. So the null hypothesis, okay, would be that my population correlation equals 0. Okay, that just means that there is no association. My alternative would be that there is a positive association. So in symbols, that would be that my alternative hypothesis is that my rho, my population correlation, is greater than 0. So you can write it in symbols or you can write it in words. So let's do another example all the way through. Now we have more of the theory down. So a professor asked her 19 students anonymously how much time they spent on non-school related activities a week, like work, family, friends, etc., and their GPA. Her hypothesis is that the more hours they spend on non-related activities, the lower their GPA would be. So she thinks that there's a negative association. So she's saying more time on non-related school means a lower GPA. So she's saying it would be something like this. So this is their time, this is their GPA, and she thinks more time means a lower GPA. So that's her hypothesis. And it might help to just quickly sketch something out like that for you. Let's see, so the data set studying in GPA is on the Chapter 11 module on Canvas. So we'll pull that up in a minute. But to start with, what would be the observational units? That would be the individual students. And there are 19 of them. The explanatory variable is the time on non-school related activities. The response variable is their GPA. And we should be in the habit of always classifying these. So time on non-school related activities, that would be numerical, that would be quantitative. And GPA, that would also be numerical, so that would be quantitative as well. The reason, again, that this is so important is when you're on the final, it won't tell you that you're supposed to be doing regression. You have to look and be like, oh, I have 2 quantitative variables. The only thing I know how to do with 2 quantitative variables is regression. And so that tells you, let's start thinking about regression and correlation. Let's see, our null hypothesis is always going to be that there is no relationship. So no relationship between time and GPA. The alternative hypothesis, we said we think there's a negative association. So we would say there's a negative relationship or association. Doesn't matter if you say relationship or association, we'll just put both. So you can see both in there, between time and GPA. Well, let's also practice writing in symbols. So for our null, it would be that my population correlation equals 0. For our alternative, it'll be that my population correlation is less than 0. Now, when you do your hypothesis, make sure you're using rho. Don't use an R because R is your sample correlation. And your hypotheses should never be about your samples. So don't use your sample correlation with R. Hypotheses are always about population parameters. So let's pull up our applet and the data set. Okay, so here's our applet. Now we can go into Canvas to actually get our data set. So it should be under the Chapter 11 module. So it should be here, this studying and GPA. It's just a text file. I just need to copy it. Control A, copy it. Come over here. Put in my data. Ooh, I don't want that thing that says annotations. Let's use data. I believe, so it's giving me an error issue. The problem was copying it out of Canvas. I think you would have better luck if you instead just downloaded the file into normal text file. But now that I deleted all the extra stuff, so it looks like it actually did. So none of that extra stuff was in here. It was just stuff that Canvas added. Let's try see if it worked. Okay, so now it worked. We have hours on the x-axis. We have GPA on the y-axis. That looks right. Okay, you can see my nice data here. Let's come back to our notes. I put it down for you. You can see the applet will tell you what the sample size is. There were 19 individuals. Okay. Let's see, if I was just to look at the scatter plot, how would I describe these relationships? So when I look at the direction, this is kind of hard for me. By I might actually think that it was positive. However, I think another person could come along and say it's actually negative. Okay, so this one was really hard to tell. So for my direction, I would say something like, I can't really tell from the scatter plot if it is positive or negative. I think you could argue it either way because the correlation is so weak. Okay. As far as strength, again, this is really weak. If you look at all of these points, could you argue that it would be just like a better flat circle than even an oval? Okay. So my strength, I would say it is very weak. You're really not getting anything super strong here. My form, well, again, it's so weak. I can't really tell if it's a line or not, but I don't see a pattern either. So we can say something like, so weak, it is hard to tell a pattern. Okay, but because I can't tell that there is a curve pattern, I can assume it's linear to do all of the rest of our stuff. Okay, now let's look. Are there any unusual observations? I mean, maybe there's a few unusual observations. Like maybe that's kind of far away, maybe that's kind of far away. But at the same time, can you really tell? If everything's just randomly scattered, can you even tell if something's unusual? Not so much. Okay, so maybe a few, but when everything is so randomly scattered, you can't really tell. So let's guess the correlation. Okay. Looking at this, again, depending on how you draw your line, like maybe it's positive, and maybe that would have been like 0.3, or if you're trying to do it down negative, like it looks even lower. This is really hard for me to tell. Really, it could just be like a perfect oval. Maybe it's just like 0. I'm going to guess that it is close to 0. And again, on the exam, we're never expecting you to get it exactly right. Like you only have to be within 0.3. Just knowing something close to 0 is still going to get you the right answer. Okay. Now, what is the actual correlation? Let's go back to the applet. Check the correlation coefficient. It is negative 0.205. So mathematically, they said it was actually going down. So negative 0.205. So in our sample, there's a slight negative association. So in our sample, there is a slight, very weak negative association. So do we have evidence of a negative association in the population of all similar students? Or could we have just gotten this correlation just due to chance based on how, sorry, that was supposed to say based on who was in our sample, assuming there's no true association. So to answer that question, we have to go to the next step. So let's use the 3S strategy to figure out. So the strategy says first you need a statistic, and we're going to use our sample correlation of r equals negative 0.205. That's going to be our statistic. Then we simulate. So we assume that there's no association, and we can just shuffle and randomly reassign GPA values to our hours, to our x values. So these are y values to our x values. So we truly mix up the y values and just form new pairs of x, y data. So we'll go to our applet. Let's change it to just one shuffle. We shuffle the y values. Notice now I get a new data set. I get a new correlation, and it's going to put the new correlation here. And I can just do this a few more times. So now I get a different correlation, different set of data, different point on my null distribution. And we just keep shuffling, and every time, notice I'm getting a different correlation, and it puts a new point on my null distribution. And I just keep going. So it just keeps changing my correlations. My correlations show up here on my null distribution. These are different shuffled correlations. And we keep going, and let's try just 1,000 times, because it does slow down our computer a lot. So I shuffle the y values, and this was stuck in it from last time. Let's come back to our notes. Because first, I want you to shade on the null distribution to show how you could find the p-value. So our correlation was negative 0.205. Okay. And if you remember, our alternative hypothesis was that my population correlation, is less than 0. So we want to shade to the left. Because it's a less than 0, we shade to the left. So let's find our correlation of negative 0.205 and shade everything to the left. So that looks like it's going to be a pretty big p-value. So to count my shuffles, I'm going to change this to a less than or equal to negative 0.205. So let's come back to our applet and try that. So we want to change it to a less than negative 0.205 and count it. So it looks like, again, that is a pretty big p-value of 0.2045. And how would we interpret that p-value? We would say something like, if the null is true, or if the null is true means really, if there is no association, then there is only or we should say only, but this is pretty big, so there is a 20.45% chance that we could get our sample correlation, it's always your sample statistic, of negative 0.205 or lower or less, okay? And I was going to say if the null is true, but I already wrote that. So if there's no association, then we have about a 20% chance that we can get our sample correlation of negative 0.205 or less. Okay, so I would say something like, that is very plausible. Okay, and so I'm not suspicious at all. I don't think we need to reject that null hypothesis. Okay. So in my conclusion, I could say something like, do we have evidence for the alternative? I would say no, we don't have evidence. So there is no evidence that there is now what was your alternative? Remember, your alternative is that my population correlation is less than 0. So that there is a negative, that was what I proposed, negative association between time and GPA for the population. Okay. So no evidence. We tried, we looked, our p-value is pretty big. There's no evidence that there's a negative association. Okay. Who can we generalize to? Okay. Well, if you remember, these are her students. It is the professor's students. So not a random sample. So we can only generalize to similar students. Can you say cause and effect? Well, this was not a randomized experiment. She didn't tell them how much time they could spend on non-school related activities. So it was just an observational study because she didn't do anything. She just observed them. She didn't control what they did. So not cause and effect.